Stop guessing where your code actually lives in RAM. You write x equals 10 or user equals user in Python or JavaScript and just move on like it's magic. But that ignorance is exactly why your backend starts crawling, why your memory usage explodes at 2 a.m., and why your app crashes under load. High-level languages hide the truth from you, and that hidden truth is costing you performance. The second your program starts, the operating system doesn't dump everything into one chaotic bucket. It carefully lays out your application's memory into structured segments. At the lowest level sits the text segment. This is pure read-only memory. It contains the actual compiled machine instructions of your code. This is where your functions physically live. Right above that are the data and BSS segments. These hold your global variables and static constants. Once allocated, they stay in memory for the entire lifetime of your program. Now let's talk about the real speed demon, the stack. The stack is clean, organized, and insanely fast. It operates on a strict last-in, first-out basis. Every time you call a function, the system pushes a new stack frame onto the stack. That frame contains your local variables, function arguments, and the return address. When the function returns, that entire frame gets popped off instantly. No searching, no drama. This is lightning fast because the CPU simply adjusts a single stack pointer using basic math. No complex operations. Just pure, predictable speed. But there's a catch. Stack memory must be known at compile time. The sizes are fixed. Go too deep with recursion or massive local arrays, and you'll hit the dreaded stack overflow. So where does all the flexible, unpredictable data go? That's the job of the heap, the wild west of your RAM. When you need memory whose size isn't known until runtime, database query results, user uploads, dynamic arrays, API responses, it has to come from the heap. Here, the memory allocator has to go searching through fragmented memory to find a free block big enough, hand you a pointer, and mark it as used. This process is slower by nature, and because memory is allocated and freed in random order, you eventually get memory fragmentation, tiny, unusable holes scattered across the heap. On top of that, languages with garbage collection have to pause everything periodically to clean up, creating those annoying latency spikes. So let's make this crystal clear. The stack is fast, automatic, and predictable, but rigid. The heap is flexible and dynamic, but slower and more dangerous. Mastering this difference is what separates casual coders who just make it work from elite engineers who design systems that actually scale under pressure. Understanding memory layout lets you write faster code, debug memory issues quicker, and build applications that don't randomly die in production.